Ladies and gentlemen, welcome to the discussion of Chapter 7 here. This is Work and Energy, and very simply, these two items are very important in physics. The first one here, which we've called work, not trying to define it or anything, but just a really big picture view of what work is how much I can get done. And again, that's kind of a corny definition. Okay, energy is, and here again, 10-cent definition, but how much it cost me to get that done. And you know, every time you drive your car, you have to put gas in it, right? It costs you something. Or if you want to run around the block, you need to eat your Wheaties, right? And there's energy that goes into your body, and then you can get some stuff done. And so these two ideas are very important with what we do in physics. They go back and forth. Here is the first one of these, work. Very simply, work is using a force to move an object. And you can see here in the formula that work equals force times distance. That's a really simple formula. You take those two numbers and you multiply them, and you get the quantity called work that we're looking for. The first one of those, force, we know all about forces. So the red arrow here represents the amount of force that I'm putting on this object. Here is a gray box that could represent a refrigerator or a car or anything, a box of books, something. I want to move it some distance. So by applying the force to the right, I move the box to the right, and if I want to see how much work I got done, then I multiply the force times the displacement. So it's a nice idea. Let's do a little example here just for fun. The box again is here, and let's say that we apply a force of 20 newtons, and I move the box some distance of let's see, we called it D, didn't we? 3 meters perhaps. So I go work equals force times distance. The force here was 20 newtons, the distance is 3 meters, and I multiply those two numbers. 20 times 3 would be 60. Newtons times meters would be Newton meters, like that. The only thing that we do here different is we call that a joule. So 1 Newton meter is 1 joule, and I would call that 60 joules would be the preferred units. Here again, every time I see a Newton meter, I call that a J for joule. James Prescott Joule, Joule, was a gentleman that started measuring energy and how much heat came out of different reactions and things. And so we remember him by naming the unit of energy after him. But 60 joules of energy here would be required to move this box 3 meters with a force of 20 newtons. And that would be how much work I would do as well. You ask, how much energy is a joule? How much work is a joule? Well, it's not very much. If you remember that little mass that we've had in our hand, the 100-gram mass would have a mass of 0.1 kilograms multiplied by 9.8 gravity. The weight of that thing would be almost exactly 1 Newton. So if I pick up that little mass that we have in the lab, 1 meter, if I raise a 100-gram mass 1 meter, that's almost exactly 1 joule, 0.98 joules. So you can see that it's a really small, wimpy unit of work or energy. But that's okay. A lot of times we have very large numbers of these things, and that works out fine. So that's all you have to do to calculate the work, as long as the force is constant and the force is parallel to the displacement. Okay? If those are not parallel, or if the force is not constant, then there are some extra things that we have to do, and I'll show you those right away. Right here, I've got 3 options. The first one of these, work equals force times distance, is the one that we just saw. when when force is constant, when the force is parallel to the displacement, everything's good, and we just simply multiply the force times the distance. In the picture here, you see that there's a man that's applying a force uphill, we'll call it. It's parallel to the surface of the ramp, and the box is moving uphill, parallel to the surface of the ramp. Those are parallel. Force is parallel to displacement, so I can simply multiply the force times the displacement and get work. In the second picture down here, there's a man that's pushing a lawnmower. His force is directed along the handle of the lawnmower down at some angle theta, and the lawnmower is moving to the right. It's moving horizontal. So in that picture, force and displacement are not parallel, and I'd have to do something a little bit different. What I really want to do is to get the component of the force that's in the direction of the displacement. So since my angle is right there, theta, if I take the cosine of that angle and multiply f by the cosine of theta, then that would give me the component of the force that's in the direction of the displacement, and by multiplying those two, then I would have the amount of work. So when the force is not parallel to the displacement, use force times displacement times the cosine of the angle between them. Some of you will also recognize that as the dot product of the two vectors, force and displacement. So that's a good place to use dot product. There's a third example here, third picture, and in this one, the man is carrying a briefcase. He is lifting upward on the briefcase, so the force is vertical. The displacement of the briefcase is horizontal in the x direction, and so there would be a 90-degree angle between those two, and since they're not parallel, then I have to use force displacement cosine theta. The cosine of theta is 0, so right there the amount of work that he does against gravity would be 0. That's a little peculiar because he is exerting a force and it is moving, but his force is only holding it up in the air. It's not causing it to move forward. We can say more about that later. The last example we'll come back to. This is for Calculus 221, the 221 class only, but if force is changing, if I have a variable force that's not the same throughout the whole problem, then I have to do the integral. And again, that's from calculus. For those of you in 201, that may not make any sense, so don't worry about it. It's not for you. But for the 221 people, we'll come back and talk about this at the very end of all of this. Okay? Let's do an example here where the force and the displacement are not equal, just to see how that works. I'm going to have a box that I'll draw right here, and I'm going to pull on it with a string that's attached. So let's put the force in here at an angle up like this, and I'll mark that with a vector sign because it is a vector quantity. But I'm dragging this box on the ground behind me, so the displacement would go that way, and there will be some angle in between the two, which we'll call theta. All right, making up some numbers for these. Let's say that the force is 20 newtons, and we move this thing a distance of 4 meters, and the angle that's in between those two vectors is 20 degrees. Okay, because the force is not parallel to the displacement, I have to say FD cosine theta. Right there, the force is 20 newtons. The displacement is 4 meters. And I need to toss in a cosine of 20 degrees, like so. So let's find our calculator here, and we'll see what that comes up to. I've got 20. Hang on. My calculator's misbehaving here. 20 times 4 cosine of 20 and that comes up to 75.2 Newton meters. Something like that. You can argue about the number of significant digits there if you want. And again, a Newton meter is simply a joule. Let's just call it 75 joules there. Okay? And that would be the amount of work that we did there. Again, this this cosine theta comes into play because the force is in one direction this way and the displacement is in a different direction there. That angle in there means get the component of F that's in the direction of the displacement. So we've done all of that now. The next thing I'd like to talk about is the kinetic energy. Kinetic energy is a simple idea. It's the energy of a moving object. If I were to take a baseball and to throw it, it would certainly take some energy to get that ball moving. If the ball hit something, it would transfer that energy to the object, and it would take some energy to get the object stopped as well. So any way that you want to think about that, the energy of a moving object is defined as kinetic energy. Kinetic energy is given by the formula that you see there before you, 1/2 the mass of the object times the velocity of the object. It makes perfect sense that the mass is an important quantity in that if I had a bigger object that was moving, it would have more energy, right? And you know, you could make the argument here, do you want to get hit by a baseball or do you want to get hit by a city bus? Of course, the right answer is neither, but all things considered, you'd probably pick the baseball, right? Right here, the velocity is important. What would have more energy, a car moving at 2 miles per hour or a car moving at 40 miles per hour? Okay, as the velocity goes up, the kinetic energy goes up, and don't forget to square the velocity there. That's an important quantity as well. So let's try a couple of these to see how this works. If I had a box here that was moving at a velocity of 10 meters per second, and we knew somehow that the mass of the box was 5 kilograms, be child's play to calculate the kinetic energy here of this thing. 1/2 mv squared, come in 1/2 5 kilograms times 10 meter per second. Don't forget to square that. I'll show you the units on this, and if you're putting the units in and watching them, you'll see that it's pretty easy to catch yourself if you do forget to square that. But that's an important part of it. 0.5 for the 1/2 times 5 times 10, and I hit the squared button right there. I get 250 for the number. And let's just look at the units here. Like I was saying, there's that kilogram, the 5 kilogram number. In the 10 meters per second, that's squared, so I'd have meters times meters. And then on the bottom, I'd have seconds times seconds. The meter is squared, the second is squared. I've got it. And what I'd like to do here is to lump all of these guys together. And you'll remember that a kilogram meter per second squared is a Newton, and then that leaves me one more meter there, so 250 Newton meters, which would be 250 joules. So that would be the answer that we're looking for right there. And that's a fairly simple problem. Here's another one we could do. Let's take the same box. And I'd like to find the velocity if the kinetic energy is equal to 400 joules. We saw that 10 meters per second made it have an energy of 250 joules. If I had more energy, it'd have to be moving faster, right? So, here's the formula for kinetic energy. This time we're trying to solve for velocity, so I'll multiply both sides by 2 and divide by m. That would leave me at v squared. Take the square root of both sides, and there would be the velocity that we're looking for. Let's put the numbers in and see what we get. The kinetic energy was 400 joules. I divide that by the mass, And I'll get my calculator out here. Slide it over where we can see. We need the square root of 2 times 400 divided by 5. The number that we want is 12.6. Okay, and let's deconstruct the units here. I've got the square root of joules on top and the square root of kilograms on the bottom. Those are kind of odd units, but let's see what happens here with these things. Remember that a joule is a kilogram, meter, meter, second, second, and then down here I've got kilograms, and you can see that the square root kilograms are going to cancel the square root kilograms there. So I've got the square root of meters squared, which would be, lost my 0.6 there, sorry, 12.6 meters, and the square root of second squared would be second. So 12.6 meters per second. We were expecting a velocity that should come out in meters per second. It did. Everything's good. So kinetic energy, very simple concept, very easy to work with. If they give you all the numbers but one, you can certainly find that number, whatever it may be. So there's that. Next topic, potential energy. I've got 3 different ways I'd like you to think about this. You can use any of them. They all apply. They're all true. Potential energy can be thought of as the energy by virtue of position. If I have an object in a certain position, or if I move it to a certain energy position that took a certain amount of energy, that energy gets stored there. And so the last one there, you see stored energy or stored work. When I do object to lift a book, where did that work go, right? As I do the work, that it has to be stored up somewhere. We call that potential energy. The one in the middle there, rather, the potential to develop kinetic energy. It has the capacity to change from that potential energy into kinetic energy. And so there's another way to kind of think about that. But all 3 of these work, and they trade back and forth. They're all the same thing. So one particular kind of potential energy is referred to as gravitational potential energy. And you can see here that when an object is raised against gravity, the work done is stored as potential energy. So I have a book sitting on the table. I pick up that book and I do work to raise it up into the air. My work is stored as potential energy. In order to calculate that potential energy, then I simply go mass times gravity times height. And so there's the numbers that we have on that. Let me do one of those for you here. The potential energy equals mass times gravity times height. So taking some kind of object right here, let's say that the mass of this thing is 2 kilograms. I'm going to raise it some height here. Let's go with 8 meters, like that. In order to calculate the potential energy, then here's what I'd have to do. 2 kilograms of mass, 9.8 meter per second squared, that's G. And then the height would be 8 meters. And I want to multiply those together. So I have 2 times 9.8 times 8, and that's 156.8. And what units would we have? Here's a kilogram meter per second squared. That much makes a newton, and then multiply that newton times a meter, I'd have a joule. So there's 156.8, 157, 160, whatever you want to call it, joules right there. I think this is an interesting formula, and let me kind of show you where this comes from real quick. How much work would it take to raise that box? If I want to raise 2 kilograms, 8 meters in the air, then from what we did in chapter 4, you remember that I've got the weight of the box pulling down. I'm going to apply a force upwards to lift that. So these would be the 2 forces that I that I need to do right there. To raise this thing at constant velocity, those would have to equal out. So the force that I need to exert is equal to mg. And if I calculate the work, like we were saying, remember work is force times distance, like that. We just found out that the work is mass times gravity. So if I plug that in, and the distance that I raise it here, we'll call h. You see how I end up with potential energy right there, mgh? And that's where that formula comes from, and why it makes so much sense. I do some work, it gets stored as potential energy, as gravitational potential energy. And that's a big idea. That's kind of neat. Here's another kind of potential energy. This is referred to as spring potential energy. And very simply, when a spring is stretched or compressed, little typo there, or compressed, the work done is stored as potential energy. And you can see the formula that they have to do that. The potential energy is equal to 1/2 kx squared. So that's our formula. Down here in picture A, there's a spring, and it's some certain length. In picture B, they grab the end of that spring and stretch it some distance x. You can see there on the horizontal part that they stretched it from position 0 over to some distance x. And the force that would be required there is kx. And they show us that the work to do that would be equal to 1/2 kx squared. Or you can think about the potential energy, 1/2 kx squared. Picture C is kind of a nice way to see that. The calculus students will see another way in just a little bit. But if I graph the force over the distance, on the vertical axis I have force, that's equal to kx. On the horizontal axis I have the displacement, x. And so it makes a little triangle there, that linear function, force function. The K there is a spring constant. Just tells me how strong a spring it is, right? If it's a little bitty dinky spring out of a ballpoint pen, that'd be a very small, weak spring. So it would have a small K value, spring constant. If it's a great big truck suspension spring, that's going to be a big strong spring. I'd have to really pull to stretch that thing, so I'd have a large spring constant. But the area of that triangle there would be 1/2 the base times the height, and you can see you end up with this 1/2 kx squared here. So that's one of those. We won't do one of these at this time, but it's a different kind of potential energy. There are other potential energies, chemical potential energies and whatnot. So lots of good kinds. Now, here is the big idea in this chapter. If I do work, it gets stored as potential energy. If I release that potential energy, it becomes kinetic energy. When that kinetic energy hits an object, it can do work on it. And so right here we have kind of a cycle of this thing, and it just goes round and round in circles. The red arrow represents the work that I do to raise it from point A to point B. We could calculate how much work there. We've done this before. F times D would be mgh. The work would be mgh. All of that work at point B gets stored as potential energy. We know how to calculate the potential energy. Again, mgh. As it falls from point B to point C, the potential energy converts to kinetic energy. It speeds up, right? And I'm getting more and more kinetic energy, but my height is going down, right? I'm losing height, therefore I'm losing potential energy. Can you see how the potential energy at the top converts into kinetic energy? And just before it hits the ground, my height is 0, effectively 0. So if I put 0 into the potential energy formula, then I would have 0 potential energy. It's all kinetic energy. All of that potential energy turned into kinetic energy. Finally, when it does hit the ground, it'll do some work on the ground. It would make an indentation there, perhaps. A lot of times in big cities, they'll be building buildings, and there'll be a pile driver. The crane will lift a big heavy object. It will do work to raise it to point B. At point B, it's dropped, converts to kinetic energy, hits a pylon, and that pylon is driven into the ground, does work, right? And so it's a cycle. It goes round and round. All of these are the same number. I cannot get any work for free. I cannot get any energy for free. It always is the same amount there. And that's a huge important idea in physics. We call that the conservation of energy. Energy is conserved. It is saved. It is the same amount. And here you see another way to say that. Energy cannot be created or destroyed, only converted from one form to another. I cannot create energy. I cannot destroy it. I can change it. I can take coal and burn that and boil water and make steam and blow that on a turbine, which turns a generator and makes electricity. Right? I took the chemical energy and converted it into electrical energy with several stages in the middle there. Okay? I converted it from one form to another, but I did not create electrical energy. I changed that energy from one form to another. The second way to say it there is energy is constant. I always have the same amount of energy in a closed system. The third way there is perhaps the most useful for what we want to do. The energy at time 1 is equal to the energy at time 2. And the formula version there, E1 equals E2, says that best of all. I can pick any 2 points in time that I want. And I am assured that the energy at point 1 is equal to the energy at point 2. So this big long thing that's written underneath that is a really nice outcome of conservation of energy. If I consider an object, it could have potential energy and kinetic energy at point 1, and it could also have potential and kinetic energy at point 2. When I get the sum of those, the sum of the potential energy and the kinetic energy at point 1, that's got to be equal to the sum of the potential energy and the kinetic energy at point 2. Let me show you an example here. This is a roller coaster. And right here, energy at point 1 has got to be equal to the energy at point 2. So I could pick any 2 points that I want. Right here at the top of the roller coaster, I've got I'm way off of the ground. I've got a big height. That means I've got a big potential energy, but I'm not moving very fast, so I have a small amount of kinetic energy. But when I add those two together, mgh1, potential energy at point 1, plus 1/2 mv1 squared, the kinetic energy at point 1, I get a certain amount. And at any other point on the track, I have to have that same amount of total energy. Let's do one of these real quick here. Here is our roller coaster, and you think about what happens as that roller coaster goes along the track here. Here we are. Yay! We'll call this point 1 up here, and I could pick any other point that I like. But let's draw the ground and measure the distance up from the ground. Let's say that the height here is 12 meters. Not a really big roller coaster, but I'm a scaredy cat, so that'll be enough for today. That cart is going to roll down the hill. When it gets to this point, it's at a much lower height, right? So here's H1. At this height, I might be 4 meters off of the ground. I've lost all that height, so I've lost a bunch of potential energy. My potential energy went down, but I'm moving much faster right here. I've sped up. So my kinetic energy went up, and the result is that the sum of those is the same. When I add those together, it would be the same. When I start back up the hill over here, I'm going to slow down, right? As I go back uphill, I lose speed, so now my kinetic energy goes down. But look at my height. Maybe I'm back up to 6 meters, right? I gained height, therefore my potential energy goes up. And again, the sum has got to be the same. I can pick any 2 points that you want to talk about there. Let's call this point 2 over here. Here's the cart at this position. And let's say that at point 2 the height is 3 meters. Okay, what I'd like to do is to find the velocity at point 2. Okay, and let's just make up a number here. Velocity at point 1 will be 1 meter per second. Okay, so I've got two numbers that are involved at point 1. I've got one that's at point 2, should have labeled that H2, sorry, and we're looking for V2. These are all related by conservation of energy, and that is the principle that we want to apply here. Conservation of energy says the energy at point 1 equals the energy at point 2. We've seen that big version of it, the potential energy at the top plus the kinetic energy at the top equals the potential energy at the bottom plus the kinetic energy at the bottom. We're concentrating on these two forms of energy. If you had other ones, then you would add them in there as well. Let's say something gets hot as you roll down the bearings of the cart. Well, that's energy too, and so you'd have to add that in. But let's not worry about it right now. Just we'll say it's all potential or kinetic, and we'll forget about heat and everything else for the moment, which is what we usually do. Right here, I have to get back to that somehow. Sorry, there it goes. Monitor slid off. Let's see what we can do first here. I've got a mass in every term, right? It's in each and every term. I could factor it out on the left, factor it out on the right, and cancel it everywhere. I'm just going to mark them out here. If it's in each and every term, you can do that. But if it's missing somewhere, please don't do that. Next up, I'm trying to solve for V2, so I'm going to subtract this term from both sides, and that will cancel it on the right hand side, put it over on the left, so I'll be left with GH1 minus GH2 plus 1/2 V1 squared equals 1/2 V2 squared. Next up, to get V2 by itself, I'm going to multiply both sides by 2. If you'll allow me, I'm going to distribute as I do that. It's not the only way to handle it, but it's what I feel like today. Okay, 2 times 1/2 would be 1, so I'll just have a V1 squared here. That'll be equal to V2 squared, and I want to get rid of the squared, so I'll have to take the square root of both sides. And right there we'll have V2 by itself. I have all of those numbers, so let's put those in. I'll have 2 times G times the height at point 1, that was 12 meters here, minus 2 times G times height 2. I'm down to 3 meters at point 2. And then the velocity at the top there would be 1 meter per second, and I do have to remember to square that. Okay, so it's calculator time here, but I think you can see that wasn't terribly painful. I come in here and I say the square root of 2 times 9.8 times 12 minus 2 times 9.8 times 3 plus 1 squared, which of course is 1, and I get 13.3 meters per second for the velocity at the bottom. These quantities are conserved. It is the same amount of energy at the top as the bottom, and so I can apply that principle and solve these kinds of problems very easily, very handily. Okay, here's another example that you're liable to see. Let's say that I'm standing here on the ground and I throw a rock into the air. Okay, so I throw this rock vertically upward at some initial velocity. I'm going to call this 0.1. So V1 is some number. We're close enough to the ground there where I'm going to call height 1 0. All right. If you wanted to raise it just a little bit, that's fine. But I'm gonna let it be equal to 0. That rock is going to come up, 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 and up here it reaches some height up there. So maybe this is 16 meters. Okay, but what you need to remember here, and the problem may not say this, so be careful. If they talk about the maximum height, then it means that that rock went up that high. It was slowing down as it went, and it actually stopped right there. The rock stopped up at the top. So V2 would be equal to 0. They might not include that explicitly in the problem, but put it in. The maximum height the rock stops. See how we can come through here and solve for V1? It's the same idea that we did before. I can come in here and say E1 equals E2. The energy at point 1 equals the energy at point 2, and you can either write out the whole big mess like this, and then you can start canceling things. Here, for example, H1 was equal to 0, so it would cancel that term out. At the top, V2 is equal to 0. This term would go away, and I'm left with that much. It simplifies down. Alternatively, you could come through here and take a little shortcut. You could say, well, there's no potential energy at the bottom, so it's all kinetic energy at the bottom, and there's no velocity at the top, therefore no kinetic energy. It would be all potential energy at the top, and you could set those equal to each other, okay, and you'd end up with that same formula that we have right there. Either way you want to go about it is fine. Write out the whole big mess, start canceling stuff out, or analyze it and say it's all kinetic at the bottom, it's all potential at the top, and set those equal to each other. Either way. The mass is the same. It's in all terms, so it looks like that. We're solving for V1 again. I'll multiply by 2 and take the square root. And the height that it rose to was 16 meters here. Not sure why it decided to erase there, but when we do the square root of 2 times 9.8 times 16, I get 17.7 meters per second. If I want it to go up 16 meters, I have to throw it at 17.7 meters per second to get it there. There's a host of these problems that work this way. We won't do this one, but here's a roofer standing on a roof. He's got a hammer and he drops the hammer. And just before the hammer falls, or maybe in the middle or anywhere else, how fast is it moving? What height was it dropped from? Any of those questions. Any problem where you can say, well, here's point 1 and here's point 2, then all you have to do is to apply conservation of energy and say the energy has to be the same at those 2 points, and do like we've done these examples. Here is another offshoot from the conservation of energy. And this is a really handy thing to have up your sleeve if you're thinking about a car or some kind of object that's changing velocity. Something had to do some work to speed that car up. It's usually the car engine. Sometimes if you run out of gas, it's you. But if your car is traveling at one speed, we'll call V0, and then it speeds up to a speed V, the final velocity there, then that took energy. right? I had to do work to make that happen. And the work here would be equal to the change in the kinetic energy. Since I don't get anything for free, and since it never disappears into nothingness, those have to be the same number. We end up with this thing called the work energy theorem. And the best way to write it is work equals 1/2 mv squared minus 1/2 mv naught squared. And that's a handy thing. Just as a little example of that, if you had a, we'll take a car here, I guess. And if your car has a mass of 1,000 kilograms and it's moving initially at a speed of 2 meters per second, and then later on it's moving at a velocity of 8 meters per second. And they say, how much work did that take? Well, you got it, right? Work equals 1/2 mv squared minus 1/2 mv naught squared. And we have all of those numbers. Oops, sorry. 8 meters per second for the final velocity there. Okay, and you'd punch it up and you'd get your number there, and it would all be good. Okay, so I won't even finish that one up. Don't want to insult your intelligence there, but you can see that that would work out. The units, I've got kilogram meter per second squared to be a Newton, times that last meter there would be a joule again. So the units work out fine. Now, we do talk about conservative and non-conservative forces, so this is a little bit of a detail here that I want to tell you about. If a force does work to move an object and the path doesn't matter, if it's the same amount of work any way that you go, we refer to that as a conservative force. It saved the energy, right? It didn't waste anything. Friction, air resistance, drag, any of those kind of things, however, do cause non-conservative forces. Friction would be a non-conservative force. So if I'm sliding a box across a table and there's no friction, then it doesn't matter if I slide it 400 meters and end up, at a distance 2 meters away from where I started, back and forth and around and up and down. If the path doesn't matter, then it would be a conservative force. If I have friction, though, it's going to take work to overcome that friction. It's going to cost me more to move it 400 meters than it would to move it just 2 meters. I've got the same displacement in both cases, but one would take a lot more work. So that's a non-conservative force, and I could talk about that. I think that's enough about that, though. Okay, next topic, power. Two ways to think of power here. Power can be thought of as rate of work. How fast am I doing work? And you can see there in the formula that that the power equals work divided by time. Or I can talk about the rate of energy. How fast am I using energy there? So in either case, it's joules over seconds. Joules per second is the unit of power. Let's do one of these. When I take, here's a box of books, and I'm going to pick this box of books up like this. So if the box of books had a mass of 40 kilograms, like that, and I want to calculate the work that I do to raise that distance of 5 meters, then I would say work equals force times displacement. The force involved would be mg, and the displacement would be h. So I'd have 40 kilograms of mass that I raise against gravity, 9.8 meter per second squared, a height of 5 meters. And 40 times 9.8 times 5 is 1,960 joules of energy that I have to expend, or 1,960 joules of work that I did. The question with power is how fast do I do that? And the faster I do it, the tireder I get, if you will. Power was work divided by time. So no matter how long I take, it's 1,960 joules of work. But you could put different numbers in here. If the time involved was 10 seconds to raise that box of books 5 meters, then I'd put my 10 seconds, and I'd be down to 196 joules per second. This also has a special unit. The unit of power is referred to as the watt. It's named after James Watt, that invented the steam engine and changed the world, literally changed the world by making machines that could do work for us, so that we're not all standing around hoeing corn. I would come in here and call this 196 watts, because 1 joule per second is 1 watt. All right, W, capital W there is a watt. So that would be the best way to write that down, 196 watts. I could do the same thing with energy there. Okay, I think this is our last or next to last slide. This really is only for the 221 people. The 201 students are welcome to listen in, but when I calculate work, it was force times distance, right? If I had a constant force, and right there in the first picture, picture A, you can see that force is constant. It's a red horizontal line that it's always the same. It's not going up, it's not going down. And if I took that amount of force and multiplied by the width of that thing, the height times the width, that would be the area of that rectangle underneath the red line. The area is the work. The area of that box, the area underneath the red line, is the amount of work. And those of you that have had 10 cents worth of calculus, they go, oh, area under a curve, that's an integral. And so what we want to do here is to integrate. If I have a changing force, then I need to take that force and integrate it with respect to the displacement. If I had a linear function here, you could see that in picture B, they've drawn little boxes here, and they've tried to slice up the area underneath that curve into little individual boxes and take the average force over that box, each little box, and multiply by the width of that thing, and then add up. You see up there at the top of that picture, work equals the sum of the individual works, and that would give you the total area under the curve, therefore the total work involved. In picture C, we could do the exact same thing, except that here we have a curved line instead of that straight line, and so that would be more along the lines of what we would normally do with integration. We have some function of force with respect to x, and then we can integrate that and to get the thing. So let me do an example here real quick, and then we'll be done. In this last slide here, I'd like us to take a force here. Let's say the force is equal to 3x squared plus 2. And I'm going to find the work to move an object let me give you two endpoints here. From x equals 0 to x equals 10 meters. All right, so here's the box initially. We want to move it over here some distance, but the farther I push it, then the harder it gets to push. Right, so the force here is equal to 3x squared plus 2. Anytime you see that function of x, then you know that you have to integrate this thing to get it. The work would be equal to the integral of force with respect to x. So that would be the integral of 3x squared plus 2 with respect to x. And you can see this is a very simple integral to do. It's a polynomial, so to integrate the first term, that would be 3x cubed divided by 3 plus 2x. And I want to integrate that from the limits, and I didn't put the limits in initially, so let me do that now. We are going from x equals 0 to x equals 10. So that's where I want to evaluate between. Those would be my limits of integration there. The 3's cancel out, so let's get rid of that. And I'd have 10 cubed plus 2 times 10. I've put the upper limit in. I subtract whatever happens when I put the lower limit in, but it being 0, that's not very interesting. So I'd have that. This is all 0. And 10 cubed would be 1,000. 2 times 10 would be 20. And so right there, I'd have 1,020 joules of work to do that. If you see a function of distance, of position, then just integrate the force over that distance, and you'll get the thing. Thank you very much. That is Chapter 7, and I'll be around if you need to ask any questions. You can email me. I'll be back in, and we will finish this up when we can. Thank you.